No explanation.
I did, Sutton. Great observation.
Yeah.
All right. We were talking about boundary conditions on Wednesday, and we walked through members and nodes, and now we started into plates and talked about how we might want to release these things and how plates are pretty, I'd say plates are kind of the crux of boundary condition establishment because they're pretty tricky. You got to really put some thought into it. One is the directions for some of these releases are a little like counterintuitive, right? Not what we might assume that the directions are. So we just got to be aware of that. We've got to consider the fact that in plates, right, they can be very, very stiff elements in plane. And so when we affect the boundary conditions for in-plane performance, we can really affect the stiffness of the model in a big way. And so we just have to be just methodical and just thoughtful on how to do this. One big thing with plates is we can do membrane action, right? You remember? What element is VA using when they do membrane action? What?
Constant stress triangle. Or is it the
Wow.
opposite?
Constant strain triangle,
Yeah.
yeah, which would be constant stress.
Yeah.
But it's not it. It's not a
the opposite
CST. Almond. There it is.
Yeah.
Almond triangle.
That big.
Yep. And when we do membrane action, we're really just removing that degree of freedom in the out of plane direction, right? Remove.
Even though the almond triangle does have that nuclear fluid, if you want.
Well, no, the almond triangle doesn't, but the thick thin triangle does.
Oh, that's right, you gotta.
Right? It's two elements, and all VA is doing is they're superimposing them together.
That's right.
Right? That thick thin triangle, all it is doing is out of plane behavior. The almond triangle, all it is doing is in plane behavior, right? It's the membrane element that's just inside or part of the thick thin element, right? Because they have different degrees of freedom, we can essentially make them one element, right? We just make the stiffness matrix a little bit bigger, and we just use shape functions associated with each one of those degrees of freedom that match whether it is the almond triangle or the thick thin triangle, right?
You're never using just a thick, thin triangle, it's like pretty
No.
useless.
Yeah, pretty useless.
Just one little-
Yep. So out of plane direction. I mean, Daniel's never gone.
He's in,
He's in
MTS. Same with MTS.
Oh, there's a thing right now.
That's for first.
Just those two.
They never emailed me to ask me if that was okay. Huh? The hell's that all about?
It's a school-related absence.
Right? We need to be careful here, though. As out of plane. Will affect load path. All right. We have a diaphragm. Say we had some joists that are framing into it. We start pushing on this diaphragm, right? We would then, if this was a moment frame, you guys have seen these, right? A little denoted with a little triangle, solid triangle in front and the back, okay? If these were moment frames, and we pushed on this, oh yeah, you're right. No, you're right. Sorry. Way to go, Madison. Chalk it up as a win
Natural
today.
plans.
Man. A little dyslexic, so it flips my world upside down. Alright, so we push on this, right? And we have the diaphragm, it might be a metal deck, it might be concrete on metal deck, it might be something else, right? When we push on this, we might put these beams, right? If these were a moment frame, it might end up doing something like right, that with our members. If we're doing that with our members and we have a diaphragm sitting on it, right, and this was say one plate element, this was another plate element, this was another plate element. That plate element's gonna be doing this, right? And if it's just truly membrane behavior, then it's not gonna care the fact that it's like moving and rotating in plane, right? But if it's a thick, thin triangle, then it does have stiffness in that out of plane direction, right? And you start bending it, and it's going to start contributing to the overall stiffness. Okay? So just something to think about is, again, when you think back to your intent of your model, does this, right, the fact that you have stiffness in the diaphragm to do this, affect the results that you're getting out, right? And is it going to more closely relate to what you think your mathematical model should be, or can you get rid of it, right? Or is it not important, okay? So you can simplify a lot of times, because a lot of times diaphragms are really just interested in what going on, like how it distributes that load in plane, right? Horizontally within the diaphragm.
So you're saying this might, like, for a diaphragm, you don't care about the in-plane? Like, you
Say
might-
a lot of times you don't, but if you were designing like
Like you don't want
that beam as composite with this diaphragm, right, you might want to consider the fact that the rotations of this diaphragm have stiffness and it's going to affect how the load's distributed. But if you were looking at just the moment frame itself and saying, okay, I'm going to apply this wind pressure on the diaphragm, right, or a line load on the diaphragm, which comes from a wind pressure, then you might not care about the fact that it's bending out of plane. You're really just trying to say, okay, how is this load coming from here and getting into here, right? And all that load's going to be in plane, right?
So you would count on VA distributing that load, you're saying you would like take those loads and apply.
Well, you could take these loads and apply them over here, but if you used plate elements, you might not care that you incorporate the thick, thin, the out of plane stiffness of those plate elements. You might just hit the box that says membrane only, and then in membrane only, it's just using the almond triangle, which means that it doesn't look at the displacements vertically.
Yeah.
Okay. One thing you also have to keep in mind is the fact that if you have, say, you take this plate and you put a uniform load on it, well, if you make it membrane only, you're going to have problems, right?
Yeah.
Because it cannot carry that load. Right? That's one of the benefits of in BA having areas. Is areas have no stiffness, right? They're just a means of transferring load, but it gives you a nice clean way of saying, okay, I'm going to put an area over this whole thing. I'm going to say that it spans one way, and then it'll put line loads on each of these members, ignoring the out of plane stiffness of the diaphragm. Then you could model this plate as a membrane only and get the behavior that you're wanting, right? Also, when you do the thick thin element and when you don't click the box that says membrane only, you're adding a lot of degrees of freedom that VA has to keep track of, right? So when you have a huge model and you have thousands of plates, okay, it can add a lot of computation time on the VA side of things.
I didn't
Right?
notice
Slow
that
things down.
membrane only checkbox.
Membrane only checkbox. Check it out.
Good thing to look at.
Check out the VA help file, okay? And like I said, it can't carry out of plane loads. No bending. Which can lead to instability, right? It can lead to instability. All right. Finally done with boundary conditions.
I think it's been 4 days.
What's that? It's been 4 days for like 4 sheets of paper.
We started on the 13th.
Wow. You keep track of that, huh? I should be keeping track of that too.
And I added it to my notes on the 5th. We were even behind when we.
When I put them out there, yeah. Oh, shit. All right, next section we're going to talk about. Okay, now that you've created this model, you've imposed boundary conditions on it, right? We need to load it, right? And then we need to analyze it. When we go to load it, right, we're going to, well, at this point when I wrote these notes, I felt like we would be moving faster. And I said, we'll review in more detail later, but need to think about some of the following, okay? And we will. I think my intent would be to finish these notes by early next week, and then we're just gonna go through and kind of give a crash course, but like some short discussion on like some main gravity elements that we model as structural engineers and some main lateral elements that we model and some of the pitfalls and things to think about when we're modeling a moment frame versus a brace frame. If you're gonna do a spread footing and you wanna incorporate bearing pressures, right? How do you do that in BA? If you do the spring stiffness, where do you get the spring stiffness from? Kind of all of those things. If you're gonna model a tank, what is that all about? Okay.
For the final and stuff, what is your plan?
It's going to be a take home.
So is it gonna be like assigned Monday of the week before?
I don't think so. I think I'm gonna give you the same amount of time. What's your schedule on, have you guys looked up the schedule for finals for you guys?
Just Monday. I know, but just,
That's Tuesday.
Tuesday. So
It's
it's
like
still
saying,
Monday,
give it
Masonry
to us on a
Tuesday.
Monday and have to do Wednesday again or something, that's gonna suck.
It'd be like assign it that week, have it do like Monday of finals.
It basically means that.
Yeah, I just like to be around for some question. What's that?
When are we supposed to meet the finals?
Wednesday.
For a tour, potentially.
We're gonna do a tour of the field house. Were you around? You weren't here. That's why. Okay. I also invited everyone to my house.
Afterwards. And then we're going to
Afterwards.
Stacy's or what?
Yeah, maybe. What's that?
Why are we going to the field house?
This is the first time.
To check it out as a tour. To look at, you know, how would we could go through like, how would you model elements in the field house? You guys,
get an invite, this is the first time hearing that.
oh, you must not have been here, son. Must have been that time where there's a
I'm stoked
bonus,
right now.
bonus problem. Right? Are you stoked right now?
Oh, yeah. I
For
wanna
what
see
part?
Field House.
Field house? Yeah.
On Wednesday.
So that was my hope, but no one at the time when I started this conversation, no one had an idea of what your finals were like. Right?
David's
What days are your finals? Are you guys
take
done
home.
on Wednesday? I'd like to like put it at the end, right? And we don't have to do it the time that we actually have scheduled to meet. I figured we could like meet over the field house at like 3 in the afternoon or even 4 in the afternoon. We'll hang out there for an hour, and then if you guys want to come out to the house, we'll have a bonfire, you know, like an hour after that. Does that seem cool?
Yeah.
Mike will be there. You can bring a significant other, okay? Does that seem fun?
No
Yeah.
one told me.
Okay.
That's
Back to the
pretty much the
idea.
final.
What's that?
When's the final?
Back to the.
So I think in,
I think I missed it.
if I gave it on Friday, it would be nice, because I could maybe walk through it with you guys beforehand, expectations, and kind of lay things out. And then, I guess, yeah, you can have it over the weekend, but I'd rather have a little bit of time to be able to answer questions more in person.
Would you be on campus Monday or Tuesday?
I'll be on campus all day on Monday. I have a final from 8 until 10
About the
Monday morning.
Wednesday before.
I think Friday's gonna be fine.
It's a dead.
It's
week.
gonna
There'll
be pretty
some-
involved, for sure, but
Oh, he's even saying like
It's not like I'm gonna
Wednesday to
procrastinate,
Friday.
I just wanna be able to have.
maybe Friday to Tuesday, yeah, maybe that works.
That way we get 3 days. to-
Yeah.
We don't do things over the weekend anyway.
So yeah, maybe that, okay,
Yeah,
maybe,
yeah,
we'll
just
see.
do it.
I'm gonna make it first,
During.
and then I'll have a better idea, but we'll plan on, I'll give it out on Friday, okay? Give it out on Friday. Does that work for everybody? But what is everybody else's final schedule? I mean, when's the steel final?
David's
Monday-
is probably gonna be
Monday.
a take home.
Masonry's on Tuesday,
Okay,
Yeah.
so that's the Monday.
so
Tuesday.
Wednesday, most of you should be done, right? Anybody planning on leaving earlier than that to go home and do whatever? Okay, so then we need to meet, okay? We don't have to meet at my house, but we need to meet during the finals week for this class somehow, okay? I've been told many times that like you have to do that.
I feel like Wednesday.
Okay, and so then Wednesday, I just thought in the afternoon, because we could just go do that and then have a little break and then meet back up. Does that work? Okay, we
Is
should
it
be able
gonna
to.
be as long as the,
What's that?
is it gonna be as long as the first one?
The first exam? Probably. But it's gonna be, I wanna do a little bit of short answer stuff, again, and then the bulk of it is going to be modeling
I would just,
from scratch.
if you
so.
haven't written it yet, just take out a few of the like redundant steps of like hand calcs and stuff. They just take time.
Yeah. This profession takes time, James. I don't know. Has no one told you this yet?
No.
Okay, I'm gonna tell you that this is hard. Okay, we get paid shit. We have a high liability. All right, you shouldn't be in this if you're looking for the easy road. Okay, that's real.
No, I know.
I'm not just saying to you. I'm saying to everybody. Like this is real. Okay. We can be sued, we can go to jail, okay?
Paid all right.
You get paid all right.
Sure, yeah, when you're first coming out and then you're like, oh my god, I'm a thousandaire, this is sick. And then like 8 years into it, you're like, holy
Wow, I
shit,
can't
this is
buy a
where I'm
house.
still at right now, I
I'm
can't
still
buy a
a
house in this
thousandaire.
town, I can't, yeah.
I feel like if you're not overworked, we make good money. Like if you
Yes, if,
work, sounds like Morrison
I
Brown,
fucking
like, no
worked my
offense.
ass off and it wasn't
sounds
worth
like they
it.
overwork you into the ground.
Yeah.
And, but
Fucking burn me out, I'm
like
done.
at DCI,
At DCI, yeah, you just come on in, do whatever, right?
they have a work-life
Yeah,
balance.
yeah,
So
show
maybe-
up, build some projects, and take off, right? I would say that yes, if you are culturally, if the company probably is better at that, and not only that, but more importantly, I'd say individually, if your personality is such that you can provide, like draw those lines, do it, and do it early, okay? I did not do that, and I got burnout, okay? I really love engineering. Hopefully it's coming across, right? I love this, I love what we're doing, but when you're doing it 70 hours a week, okay, not fun, right? And for like, not like working for months straight, not fun, right? Every day, just not fun. So you
They pay you
gotta,
overtime though, right?
if the project had budget for it,
Really?
yes. And you only get paid, you only get paid straight time,
Not time and a half.
because we're professionals.
Yeah.
Did you be wearing the year bonuses?
We did.
Okay.
Yep. But it didn't really make it up. I don't know. Yeah, I tell you, so like, I have no problem telling you how much I made, right? So 8 years in, okay, the last year I worked, I made just over 100 grand. Okay? Seems like a lot, right? Maybe it seems like a lot. But like hourly rate wise, it would probably wasn't that great, right? I was making almost 40 an hour. My yearly bonus was about, I think it was like 8 grand, okay? My base salary, like up to 40, right, was somewhere around 80,000 a year, but then adding in some of the overtime hours, you know, it starts to tick up, but it wasn't equitable. It did not, I mean, it maybe sounds like an amazing, you're willing to work 70 hours a week. I was too, right? Also, when you start, we're getting on a tangent here. Also, when you start, like, you're adding value to yourself, like, significantly, right? And the time you've put in, you're going to get that out, right? It's gonna pay dividends, okay? I was also paid at like a 13 to 15 year sort of person. I had responsibilities at that level. I was managing, you know, $500,000 of projects a year. Like, there was things because I was working so much, but it's kind of a trade-off, right? So you can, and so I'd say definitely like your first 4 years or 3 years as you guys are like getting ready for the PE, like if you put time in, like you're gonna get a lot out, okay? But it's a slippery slope, okay? Slippery slope. Will I go back? Maybe. Maybe I'll go to DCI if they'll have me.
We don't have any room.
Oh, shit! Damn, I'll ask Sam today. Can I get a job, Sam? Pull up.
You're gonna
But yeah, we do make good money, right? And I'd say, especially when you get licensed, like that's something they have a hard time taking away from you, and it affords you benefits, right? Like I still design stuff out in the real world, okay, to this day, and it's awesome, okay? And not a lot of people can do it, right? Put your name on things. So. Good? All right, but it's hard. There's a lot of liability, right? Okay. So when we do an analysis, right, and we devise a model that's matching the mathematical model, which came from the real world, right, we get to this point where we've imposed boundary conditions. We think that our model is supported adequately, that matches what we expect, right, or what we want to a model. We're doing that all with the intent of designing something, right? And so that model can change depending whether, as I just discussed, we're modeling this joist or whether we're modeling a foundation underneath the moment frame, right? So when we think about loading, we got to think about the source type, right? Is it dead load? Is it live load? Snow load, right? Really all of these gravity sources. We have seismic. We have wind. Right, some of those lateral sources, right? We could say soils can be in the lateral category also, right? Some loads that maybe are not as explicit, right? We have our load combinations, our LRFD and ASD load combinations, right? They say 1.2 dead plus 1.6 live, or all of those things, right? There's some loads that you're gonna face in the real world that are not going to explicitly just land within one of those categories. One good example of that is if you ever do pre-engineered metal building design, they have dead loads, and then what they have is a load called collateral load. Collateral load is just saying that over the course of the life of these, warehouses, people might start attaching random shit to the walls and the roof. And so you end up adding like 2 to 6 pounds per square foot, or there's on the walls or the roof, to account for this added dead load, right? Well, if we're doing overturning, we might say that this building's brand new and it doesn't have any collateral load, right? And so if we're looking for the worst case, say uplift, we might ignore it, okay? But then down the road it might be there, so then we might include it in the seismic calculations, right? And so we kind of have to think methodically about, okay, what load combinations should we add it in? What load combinations should we pull it out of? When is it there? When is it not there? So I just say collateral. I gotta say, Morrison Merrily is a good company though, okay? Don't make it sound like it's not a good company.
I do like, you guys have like ownership, right?
Yeah, it's awesome.
That was the other thing you talked about
Yeah,
before.
it's like I have $100,000 from my 8 years there that I own of that company, right? And it grows every year based on everyone else still working. It's an amazing thing. They get to know the stock price today, and I've been texting them like, all right, let me know how well you guys did last year. I want to know how much I'm worth, right? So yeah, because then making 100 grand, a little over 100 grand, I still got about 20% of that salary was in stock. So I'd get a $20,000 check that went somewhere else. So really I was making 120. So I mean, there's some significant extra stuff there, I guess, right? So collateral loads, another ones are impact loading, right? How do we consider impact loading? What's the magnitude of that? Just there's things that are kind of outside the box, right? Everything doesn't just land within this nice, clean set of load combinations, okay?
If you go into the whole bridge design, there's the.
Oh, AASHTO is ridiculous. Yeah, AASHTO is ridiculous. Not a lot of fun, okay? When we think about magnitude of these loads, well, sometimes we might want to consider them. Sometimes we might be able to ignore them. Ignore some loads.
I remember once hearing like with load combinations to not double dip. It was like stuck in my head so much, like you can't double dip with load combinations towards like you gotta stick with one and that's the one like and I feel like
Double dip with load
have you ever heard
Like,
that
you can't have a
in
max
masonry?
this and a
I
max
swear
of
we
that.
heard that, and like ever since then I've always been like, well, I feel like I should design this with this load combination, and then I should design this other member with this load combination because it gives me the highest. Or like for one member, like would I design the moment for this load combination, then I design the shear for this other load combination that gives me max shear, and then I design it for
Yes.
max axial load combination. Right, use
You get your envelope.
Yes.
So that's
Max,
like-
right? I mean, like,
triple dipping all those-
You're looking at
all
max.
these dips.
Maybe the one thing, maybe, are you saying,
Like load reductions.
if Audrey said anything about that, is probably what she was meaning is there could be, I gotta put this.
Because it was like two
Like,
and a
if-
half years I took it, so I like don't.
I would just say that if
phrase,
if there was a connection between the shear strength and moment strength of an element,
Sure.
right? Then you might want to consider like, okay, I'm gonna design it for this load combination. It might be the max moment, but that's tied to some shear demand also, right?
Right.
And so then I design that member for the connection of those two, because for the capacity of the member, those things are connected in some way, right? If you're designing it like in steel or even in concrete, right? The moment capacity is like independent of the shear capacity, right? And so like you wouldn't want your member to fail in shear, and you don't want it to fail in moment, but those are dependent. So you would want to look at, okay, when I design it for moment, I'm going to look at the worst load combination for the worst moment. And whatever the shear is at that point, I don't give a shit, because I got a maximum one that's in some other load combination that I'm going to design that beam for.
Yeah.
And it's automatically going to be okay. Does that make sense?
Sure.
But if you had like a weld that you were designing like a plate that was welded against another plate, okay? And this plate had moment and shear on it, the weld that you design is gonna have both the moment, right? The T and C forces in the weld, plus it's gonna have the shear forces in the weld, and they interact, right? And so it'd be very conservative to go through and go find the maximum shear from one combination and the maximum moment from another, and design this connection for both of those magnitudes.
I feel like more commonly like moment and axial, like counting on a
Same
max
thing
and
would be-
axial.
that would
like
work in the-
reduce your moment or like.
Yes,
increase it.
so definitely like with
So maybe
columns,
there, yeah,
like PM interaction diagrams,
Exactly.
there would be a function because, right, because you're,
So you can't go max axial, max.
yeah, it
moment.
does something like this, right?
That would almost be unconservative sometimes.
Yes,
yeah.
for sure. We got PMN, right,
So
and
maybe that's
PPN,
what-
and you're gonna plot your PU and MU somewhere in the middle here, or MU, PU, right? And so, yeah, if you grabbed worst case, but because of this behavior, right, if you did this and you said phi, and then you did a linear interaction, right, this is a non-linear interaction diagram. If you did a linear interaction diagram, which is conservative, then you could do that. You could just say maximum, maximum, plot it. If it was inside this, you'd be okay. But the fact that you have this weird thing going on, that axial load, it might kick you up here above the curve, right? This NU, PU, can you see this? NU, PU, right, is right here. But if you use the actual moment at that moment demand, you might be down here and it might not be okay, right?
Sure, yeah. So that.
There isn't a cookbook, okay? Again, this is hard, right?
I
You
feel
just
like
gotta think
load
about
combos
it.
are harder than like they should be a lot of times.
What's that?
Load combinations, like they trip me up a lot of times where it feels like it should be so simple, like you should
Yeah.
choose one, like actually choosing the right loads is like.
And that's where the modeling is very helpful, or like,
Yeah.
we lean on analysis programs. I mean, not just visual analysis, but like other like post-processing ones, where we can then say, all right, I'm gonna do this by hand, I get my like service cases, dead, live, snow, wind, all this stuff. I put it into a software package and it's gonna design me this one beam, and it does all the combinations for me.
Right.
Right? And then checks all the code requirements for me. Right? All right, so you can ignore some loads, right? We might have to refine the model a little bit, like we talked about when I gave you the example of the write-up for, I think it was either Norm or Building X, right? Chris Van Lucian had done, where he explained kind of what he was doing with the nodes, and we essentially took some of that load from the model and lumped it into locations, right? So we might change the magnitude or ignore the magnitude or move that force in order to like better model, right, our, like the intent, like model our design intent, whether it's the brace frame, moment frames, supports, or whatever. So as I said, distribution wise, we might manipulate that. It might be a point load, it might be a uniform, might come as a pressure, might be a line. Wind loading, you could use any one of these, right? You could put a pressure, like the homework, right? The stair tower, right? If you had something that could distribute the pressure from the wind vertically, you could load, say, plates or areas on the side of that stair tower, right? And then have it distribute it to all of the diaphragms, right? Or you could do a line load, assuming a distribution between diaphragms. You could come up with a magnitude and run that line load across the entire structure, right? Or you could say, I don't even care about that. I know it's gonna distribute, you know, maybe simply supported, right? Half trip each way to the diaphragm, then half trip from each grid to each grid. Then I could put that as a point load on the end of my frame. Or I could put it as a linear load along the frame, right? You can make all of those assumptions. And it all comes down to what is the intent of your model, right? What are you trying to get out of it?
Why would you not feel good about just turning it into a line code and putting it on there?
If I was like interested in, like there was a shear wall on the outside of the building and I wanted to incorporate the fact that there's out of plane loading on it, like Cobley Hall has big shear walls at the stairwells, right? And so some of those walls are taking direct wind pressure, and they need to carry that while maybe getting a wind load the other way where they have, you know, inline, in-plane forces acting on it.
Okay, so you
Right.
put that as wind pressure on the shear.
So then, yeah, you could put it as a wind pressure on the edges of the
You
shear wall.
do sometimes account for the lateral stiffness in the out of plane direction of shear walls.
Yeah, sometimes you could, for
Like,
sure.
like anything we've done in like school has been like ignore all stiffness out of plane of shear walls, like count on everything that's, you know.
Yes,
in that direction.
I would say that, you know, you are looking at it, if you were designing that individual shear wall,
Like if
right?
it's an outer.
But if you were
exterior
looking
wall,
globally at the entire building and what's going on, I would probably do a line load, right, and do an analysis ignoring some of that local behavior and local forces. And then at the end, when I went to designing that actual wall, then I'd start thinking, okay, what other loads are on this that I ignored when I created this analysis in the first place, that I should probably put on this now. Load sequencing is a big one, tanks. Construction. Did you guys talk about tanks and concrete? For those of you who've already taken the second concrete. Yes. Concrete tanks? You guys didn't talk about concrete tanks?
What do you mean by that?
Like, City of Bozeman has like 1,000,000-gallon concrete tanks that are buried in the ground. Yellowstone Club, like millions of gallons. Like you go up to, well, it's Lyman Creek, which is over by the M. That's where some of the drinking water for Bozeman comes from. Okay, they collect it and they put it in these big tanks. And Yellowstone Club, Spanish Peaks, right? They need to provide pressure and volume of water for everybody that's up there in Big Sky. So what do? They pump water out of wells and they put it in a big storage tank way up on the hill, right? We get hydrostatic pressure from that. It's like Belgrade's water tower, but you use natural topography to get it, right? Instead of putting it up on a tower, you're just putting it up on the hillside, right? So you gotta design for that. Any thoughts about how that works, right? Or how we would, I mean, what would be important about sequencing of tanks?
Because before you have like the water pressure pushing against the walls, it's against the soil pressure.
Yep.
But then, so you gotta like have an empty tank,
Yep.
with full soil pressure, but then you can count on it to push against the
So
soil.
before you even do that, if you were going to build a tank out of concrete cracks, right? And you're gonna fill it with water eventually, is there something you might wanna do before you even like put the soil against it?
Post-tension,
Yeah, there's post tensioning that happens sometimes.
a lot of clear cover.
Just test it to see if it leaks, right? And like fix leaks if it is leaking. I mean, it leaks, like they leak, but there's an allowable amount of leakage that happens in those tanks, right?
Depends on what you're.
It's made out of
holding.
concrete, unless you post tension it, and then there's the ability to like suck it all together and there are no cracks, right?
So I use UHBC.
You use the UHBC and you go bankrupt constructing it, right? So yeah, it's you know, you have no soil pressure, you have all the water in it, and that honestly is usually what designs the size of the tank. Because you get this 62 pound, you know, 62.4 pounds per square foot per foot height of these walls, right? And a lot of times soil pressures is like somewhere around 40 to 60. So, you know, and then at that point you assume that it can be full or it can be empty, right? So sequencing can be big. I mentioned it once on Norm, right? When we designed it, the first floor that sits on Grant, yes, 3rd and Grant. I lived on 3rd and Grant. That's how I always remember that. Grant. So Grant Street, right? That first story, the second story is set back from it. So the next 2 stories sit on top of these big girders, right? And so we had to think about the idea of when are they going to pour concrete on all the subsequent decks, right? I mentioned that there was a problem. I can't remember what building it was, but there was a problem where we camber the beams and we over cambered them to try and make up for the dead load deflection, but we assumed that there was going to be more weight on it than there really was based on the fact that the construction sequence that they were choosing, right? We assumed that all the dead load from all the diaphragms up above, they had poured all the diaphragms. We just used the dead load like in the homework, 60 pounds per square foot. We said that that was there on that column sitting on that girder, okay? When it really wasn't when they went to pour the floor. So then all these studs are sticking out of the concrete, right? Not good, right? Not good. So you gotta think about load sequencing, right? So then not only are we thinking about the load combinations that are controlling, but then whether or not we're going to have loads in those combinations at given times, right? Going back to the collateral loads, that's another example of that.
You can't specify construction.
You can, but it is frowned upon because that really starts dictating means and methods, which is like how a contractor is going to build something. And they like to have ultimate freedom in that capacity because that's where they can be competitive in bidding. So if they come up with some grand idea or they did a project before in a certain way and they have all the materials and the tools to do it, then they'd like to bid it that way and hopefully it'll give them an edge, right? And that will reduce the project cost. The more and more you constrain it to a specific path, the more cost you're likely going to impose.
Well, unless you're ripping out a ton of concrete, 'cause-
What's that?
unless you're ripping out tons of concrete. 'cause-
Yeah, I mean, like you build a tank, you have to test it, right? I
Well,
mean, there's some of those
that's what
sequences.
you were saying, like.
What's that?
And then rip all that out because.
Oh yeah, the camber, yeah, for sure. Yep.
Yes, that also raises costs.
But so you end up just upsizing the beam so you don't get as much deflection in the first place, you know, which adds a little bit of cost, but then the contractor doesn't have to think about that, right? As they move through it. Connections and load path, right? Force transfer, force transfer mechanisms. We gotta think about, well, it's not on this set of notes, but that fillet well on the one side of the plate, right? How are those loads getting transferred from one place to the next, right? It's like in concrete slabs, a lot of times, like this was a concrete slab. Did you guys do concrete, like slab on grade design? In concrete?
I feel like we did slab design, I don't know if it's like slab on grade
Fuck.
specific.
Like did you guys talk about like the Army Corps of Engineers or the Portland Cement Association and how they design slabs and some of the requirements? No slab design, don't remember that. So you don't remember that.
I don't think we did. any
Emily's
slab
like
design.
nodding, did you do slab
I
design?
went
She's
to
doing-
different school.
Oh, okay.
She did
Definitely
undergrad
did.
slab.
Hey, a better school,
Because
right?
I did
That's
at
what you
work,
say.
and I was like, shit, I don't know how to do this.
So you end up putting joints in the slabs, right? Because concrete cracks, it shrinks, right? We can put control joints in the slabs, we have construction joints. Obviously, they can't pour one big continuous slab, right? There's a limit, right? So we end up putting joints in it. Well, at these joints, sometimes, right, we might have it where we're gonna have a joint that goes across here, and we might put a dowel across it, okay? And that dowel across it, we might have it deformed, right? Just take a piece of rebar, we're gonna put it across the joint. Well, that rebar is going to transfer, right, vertical forces, and then it's also gonna keep the slabs from pulling apart. Well, in some cases, we might wanna just put a smooth dowel, right? We might put like a 1-inch square solid stock or 1-inch round stock, and then actually have the contractor grease one end of this when they put it in the slab, so that the slab can move around. So we're not restraining these cracks, right? But then it allows this thing to transfer up and down. So, you know, you gotta think about force transfer and connections and load path and how we're allowing things to move and transfer from one thing to the next. right?
I feel like
What's
we did
that?
somewhere, I can't remember.
Oh, see, there it is, coming
I
back.
don't remember when we did that, but I did that.
Blow some dust off that.
I was gonna say, I
What's
think
that?
that was structures too.
Structures too. Did it?
Yeah, I just gave a
Elevated
lecture on
slab design. This is, I'm talking about slabs on grade.
Yeah.
We have a full lab lecture on like, well, not a full lab lecture, but there's like a talk about.
Slab
this
on grade.
exact
Okay, we talk about control joints and construction joints and
thing.
stuff.
And dowels.
And downs, yeah, yeah. Okay, yeah. Yeah, so you guys got it. You got it one day, right? What's another thing with loads? Well, second order effects. P delta, P little delta. We have code requirements we gotta consider. We think about loading. You guys are doing brace frames right now. I keep assuming you guys have done stuff and you haven't. So I'll just tell you that, right, the seismic manual requires you to do certain, well, it requires you to do certain analysis with respect to forces on brace frames, right? And assuming you might, like when you're designing the columns for them, you might have a model with which all of the braces can only hold forces in tension and none in compression and stuff like that, right? So there's code requirements that require us to do stuff. Aaron was talking the other day about creating this frame on the end of the building, right, to do some of the stability checks in the seismic manuals, right? Yeah. All right, analysis. So you impose all these boundary conditions, you think that it's, right, matches your mathematical model, right? It's geared towards getting something out, right? Your intent, and this is where you cross your fingers and assume and hope that errors don't show up, right? And you get what we call accurate results, right? We're gonna try and match our mathematical model. We're gonna try and model something that we're going to feel good about the results that we get out of it. Well, the programs vary in their process for running an analysis. How does RESA do it? Yeah, so like, I guess I would say it can affect, we'll jump through this real quick. Can affect your modeling, workflow, some models or some analysis programs do simultaneous analysis. Some of them do initiated analysis. Simultaneous means if you change something in the model, VA right now, the way it's set up, it will simultaneously go through and run it, right? So then when you click on the results tab, something might not show up immediately, but when it's done running its analysis, the results are gonna pop up. Immediately change something, immediately it affects the results, right? Initiated analysis, you change something in the model, it doesn't run it until you hit run, right?
In SAP, it makes it so you can't make changes if it's like locked, and then you have to unlock it, make the change, and then you have to run it again.
Yeah, and so do you have to be deliberate in telling it to run?
Yeah.
So like VA used to be that way, and it could create big problems, right? Where essentially you had the model view, you changed something, but in the results view, it had run your previous analysis. So if you changed a member size or changed a few boundary conditions, right? Might still be stable, right? It might, maybe it wasn't the intent of what you originally decided to model, so you change a few things. But if you jump to the results view without, say, either putting your previous results in the trash or rerunning the model, you could easily just jump to the results and be looking at the results that you previously had.
So in RESA, you have to initiate it, but it gives you a
Warning.
if you change.
Okay.
If you're gonna change anything.
Yeah.
That'll affect your results, it clears them.
Oh, it does, yeah, okay.
It's like
See,
warning.
VA used to not, I mean, this was
Yeah.
quite a
But
few
yeah,
years
you
ago.
hit run every
Yeah,
time you want.
and I'm assuming that most of them are doing this. I just wanted to bring up the fact that it's possible, right? Where you could be looking at bad results or previous results. You just have to be careful about how is the program making that step or initiating its analysis, okay? Adam swears up and down. The one problem I have with this is that I wish there was a button where we could shut off the analysis, because I feel like it's bogging the computer down. Even though Adam swears up and down that it takes this and it puts it on different cores in your processor, and so that it's really not affecting the operations of modeling, but it does, right? Do you feel that way sometimes?
I would imagine it would.
Right, because sometimes you have a big model and you start changing a few things, it bogs down because it feel like it's trying to especially when you have tons of areas and you change grids, and it has to redistribute all those loads, and it immediately does that the second you move a node, right? And so it's constantly trying to work while you're trying to change the model, and if it's big enough, then it's just churning and churning and churning. And so I tried to tell him, I'm like, just give us a button that says turn analysis off, and then just let me model it, and then I can turn it back on. And he said it's not needed, so.
RIM isn't like that.
How-
Like, you can just model, change things,
Yeah.
and then tell it to analyze.
And so it does like RISA does, where it wouldn't give you results until you tell it to analyze?
Right, and if you go to change something, it'll say, this, it will need to be reanalyzed, you know, like
Oh,
the
okay.
analysis will
Yeah,
be
yeah, yeah.
updated. So it's just like the separates.
Yeah, yeah, separate, okay. Okay. Well, good. So you need to be careful not to use old results.
So going to the results tab doesn't initiate all of that,
It automatically does that. You could be in the model tab, the second you start modeling, it's trying to analyze it.
I noticed that.
Yeah. So like if you put one node out there and you jump over to the results, it says model's not stable. Draw beam,
That
2
happened
nodes.
even before you clicked on the results tab.
Oh, you're getting real deep here.
'Cause that feels like a run button, it's just like
It's like-
results tab, that is the run button.
Does a tree make a noise when it falls over the forest and no one's there to hear it? Right?
It seems like the same thing to do.
Yeah.
It's not like we click it and then it shows the yeah.
It only runs it like if you've made a change already.
Those results are there.
Yeah, but like if you don't
Once
make
you
a
click
change
the
and you go back and forth between model and results, it doesn't reanalyze everything?
No, it's not reanalyzing when you're going back and forth. It just
Only when you
analyzes.
make a
I'll
change.
believe it.
Yeah, it's only when you make a change. But if you just, when you first start a model and you put in a node, it's trying to run it. It's trying to get you results. Whether or not it is able to run it, it's gonna say model's not stable if you just had a node sitting there in free space, right? That leads us into the next, fuck, we almost made it through this.
I know.
whole
Yeah,
node
we're
set.
distracted.
Yeah, a little bit, but I think it was good.
Did better, better, good job.
Thank you, appreciate it.
That was good.
Appreciate it.
Aaron wasn't here, so.
Yeah. Yeah.
We just finished it, we got 2 things.
We can,
Yeah.
if it's just right.
Whoa, you guys wanna stick around? I'll stay here all day, this is sick. Alright, let's just finish this, The last thing I wanted to say here was, right, we need to be sure to check our analysis status and notes. So like RISA, RAM, when you go to the results thing, it says, hey, you changed something, right? You need to rerun this, or don't use these results, right? Well, even when it does run it, like VA runs it, and you guys have been exposed to with the homework, right? It says model isn't stable. It says there's too many load combinations. It says that your deflections are excessive. It says your design results are fucked up, right? It has like all these little warnings for you, okay? And there's different, in VA, there's different like color coding of what that means, all right? So there's like orange, which is like shit isn't right. Yellow, it runs, but there's something else wrong, okay? That doesn't, if it runs, that doesn't mean it's good, right? Make sure you feel comfortable with all of what it's saying on the right-hand side, right? And you look that up and you understand what's going on, right? These notices, right, or statuses can indicate sources or source. Whoa. Got a little crazy here. Sources. A source or sources of analysis errors that need to be reviewed before, all right, big thing here, before using results. Okay. One of those examples that Adam brought in where that guy had 7 light years of displacement, right? Okay, if that, like, it said in the error that they had excessive displacement, right? Did not look at it, okay? Some of those are the big ones, like VA will say, okay, the overall model size is 100 feet by 100 feet. If he gets a displacement that's more than like 6 inches, right? Or maybe even like 3 feet, it knows that something's fucked up, right? Because we're doing a linear elastic analysis, right? Everything's gotta stay pretty linear. And then to get those displacements out of general structures, right? Things are gonna go nonlinear. Another thing that it checks, which it will run, is if, like, it knows the materials you used, so it knows what the yield stress of that material is, right? So it figures out the stresses in all your members. And so if a member goes beyond yield, it's gonna give you a warning because it knows that, hey, we're assuming linear elastic, but the results you're getting is assuming that it's linear elastic beyond the yield. In reality, it won't be, right? And so the model's not accurate. And so a lot of those things come up. But will the model run? For sure. Sometimes it might be beyond stress. It might be at like 60 KSI for a W section, right? It's not that far beyond yield, okay? But the model will be inaccurate, right? And displacements might seem okay. And the little color code, it might be yellow, right? It's like, hey, I don't know, you're the designer, not me. Just saying, it's beyond yield, right? And you can use those results. Check. Even if your model runs. It might be a simple like post-processing problem, right? Not necessarily with the finite element analysis portion, but when it takes those results and moves beyond it and it's gonna design a steel beam, well, maybe that steel beam, you have load combinations for LRFD, but then when you actually design the beam, you have it designed based on ASD, but it has no load combinations to grab for ASD, right? Because you never analyzed the ASD load combination, okay? It can be that simple, but understanding what is wrong or what they perceive as wrong is critical. That's it.
Did it.